Hello, this is Meteorology 113, Lecture 1, Atmospheric Structure and Composition. This is the first lecture of Course Module 1, the Natural Unpolluted Atmosphere. The outline of this lecture is as follows. First, we will cover the vertical structure of the atmosphere. Specifically, we will see how atmospheric pressure, density, and temperature typically vary over the depth of the Earth's atmosphere, and how as a result of this, we can classify the atmosphere into distinct layers, each with unique characteristics. We will next cover the composition of the atmosphere, focusing primarily on the percentages of its constituent gases. Finally, related topics will be covered that reinforce understanding and present important consequences of atmospheric structure and composition. This will help prepare for later lectures focused on air pollution. Atmospheric structure. Seen here is a photograph taken from space of the Earth's horizon, showing a cross-section of the Earth and its atmosphere with space and the moon in the background. The atmosphere is the light blue layer running along and above the Earth's surface. The light blue color is due to scattering of sunlight by atmospheric gases, which is strongest for blue light. The thickness of the atmosphere, in terms of when atmospheric gases are first encountered from outer space, is around 500 kilometers. This is about 5% of the diameter of the Earth, which is around 13,000 kilometers. In this slide, we show the vertical variation of two variables that describe the atmosphere: density and pressure. The chart is a vertical cross-section of the atmosphere, with height on the vertical axis increasing upward from the surface to the top of the atmosphere at around 500 kilometers, and density and pressure are on the horizontal axis, increasing to the right. The density of a substance is the amount of its mass per volume. Air density at the surface is typically around 1.2 kilograms of air per cubic meter. Air pressure is the weight of the overlying atmosphere atop a given area. Air pressure at the surface is typically around 14.7 pounds per square inch, as depicted by the graphic shown to the right of the vertical density and pressure profiles. However, both density and pressure strongly decrease with height away from the surface, as can be seen on the plot. In fact, about 90% of atmospheric mass is within the first 20 kilometers or so above the surface, although the top of the atmosphere, when atmospheric gas molecules first start to appear from outer space, is around 500 kilometers. In fact, around 50% of the total mass of the atmosphere is contained within the first 5 kilometers. So although atmospheric gases exist up to 500 kilometers above the surface, the bulk of its mass is a much thinner layer. Compared to the Earth's diameter, this thin layer is like the skin of an apple. The other key thermodynamic variable is temperature. The temperature of a substance is a measure of the average speed of molecules within the substance. This molecular motion is due to something called Brownian motion, which is the random molecular motion within an object at a certain temperature. There are familiar ways of expressing temperature of a substance, for example, degrees Fahrenheit or Celsius. The Kelvin scale is another scale set such that the value of 0 Kelvin corresponds to 0 molecular motion. 0 Kelvin is therefore the coldest an object can be. this slide, we show the vertical variation of temperature across the atmosphere. The chart is a vertical cross-section of the atmosphere with height on the vertical axis increasing upward from the surface to 120 kilometers, and temperature is on the horizontal axis, increasing to the right. Temperature is expressed on the plot in terms of both Celsius and Fahrenheit. Whereas density and pressure smoothly decrease with height upward across the atmosphere, temperature, as can be seen on the plot, has a much more variable structure. Specifically, 4 distinct layers can be discerned, where temperature alternates between decreasing with height and increasing in value with height. The lowest layer, roughly within the first 10 to 15 kilometers above the surface, is called the troposphere, where temperature typically decreases with height. This is the layer where Earth's weather and major climate systems exist, and of course is also where we live. In this sense, the troposphere is the most important layer and will be the focus of this class when we study air pollution in more depth. Above the troposphere, extending upward from around 20 to 50 kilometers, is the stratosphere, where temperature typically increases with height. A layer where temperature increases with height, or warm air atop cold, is called a temperature inversion. The warming of the air with height in the stratosphere is due to the presence of the atmospheric gas ozone, which absorbs ultraviolet sunlight and therefore acts as a warming agent in the stratosphere. The ozone in the stratosphere is called the ozone layer. We will discuss this more in the next lecture. Above the stratosphere are 2 layers that collectively comprise what we call the upper atmosphere, the mesosphere and the thermosphere. We will not focus on the upper atmosphere in this class beyond this lecture, but it is a very important layer in other respects, as we will cover later in this lecture. Atmospheric composition. We now turn attention to what the atmosphere is comprised of and in what percentages. First, it is important to understand that the atmosphere is a mixture of gases of different chemical compounds. That is, there is not a specific chemical species that is air, but instead air is a mixture of gaseous species. Among these are water vapor, or water in the gaseous phase. Second, the atmosphere is comprised of hydrometeors, or water in liquid or solid phase that form when from condensation of water vapor. These include clouds, fog, haze, rain, and snow. Finally, the atmosphere is comprised of what we call aerosols, or solid or liquid particles of various chemical natures so tiny in size that they stay suspended in air. Aerosols include dust and smoke. In fact, among the most dangerous air pollutants for human health are smoke aerosols, also called fine particulate, as we will cover later in the semester. We now focus on the gases that comprise the atmosphere. We will focus on what we call dry air, which is air excluding water vapor. The way to think of this is to imagine taking a sample of dry air, separating it according to chemical species, and recording what percentage of molecules would be of each species. A pie chart of the result of such an exercise is shown here. It is seen that overwhelmingly the composition of the atmosphere is of 2 main molecules, diatomic nitrogen, or N2, consisting of 2 nitrogen atoms in a covalent bond, which comprises 78% of the dry atmosphere, and diatomic oxygen, or O2, consisting of 2 oxygen atoms in a covalent bond, which comprises around 21% of the dry atmosphere. For simplicity, we refer to these gases as simply nitrogen and oxygen, understanding that the specific species are diatomic pairs of these atoms. The remaining 1% is comprised of the inert gas argon and an even smaller percent that is a mixture of everything else that can be in the air, which includes any air pollution species. We refer to these as trace gases. A typical composition of the trace gas mix is shown here in the lower right of the pie chart. As you can see, several gases that may be familiar to you, including carbon dioxide at 0.035%, which is important for climate change, and on the bottom of ozone at a very small percentage, which is mainly in the stratosphere, comprising the ozone layer that we discussed a few slides ago. So some key points. First, nitrogen and oxygen make up most of the atmosphere, in combination around 99% of dry air. Water vapor, if included in the mix, would comprise anywhere from 1 to 4% depending on whether we are sampling in a humid or not so humid location. Carbon dioxide at 0.037%, which we can conveniently express as 370 parts per million by multiplying the percent composition by 10,000, is shown there as the third bullet. In fact, CO2 concentrations currently are higher than this, around 410 parts per million. The amount of gas in parts per million can be interpreted as how many molecules exist of a given species per million molecules of air. Likewise, the amount of gas in parts per billion can be interpreted as how many molecules exist of a given species per billion molecules of air. Expressing concentrations as ppm or ppb is useful for trace gases, which have very low numbers if expressed as a percentage of the atmosphere. The remaining trace gases comprise a very low percentage. They are not listed in the lower right of the pie chart. This slide gives a more detailed look at the gases that comprise the atmosphere. The table has 3 columns. On the left column is the species. The middle column then gives typical concentrations in the atmosphere of these species, or a range, expressed as percentage or parts per million or even parts per billion if very small. The right column then gives a description of the sources of these gases, which we will not cover at this time in the lecture since we will cover this later in the semester. We can classify this list into broader categories. First, we indicate the 3 main species, nitrogen, oxygen, and water vapor, which comprise most of the atmosphere. Then, there are a class of what we call inert gases, which are a single element rather than compounds. These include argon, neon, helium, and krypton. Inert means non-reactive, and hence these gases do not react with other species. We then indicate 2 important gases that are among the mix of greenhouse gases in the atmosphere: carbon dioxide and methane. A greenhouse gas absorbs infrared radiation, or heat energy emitted by a body, yet largely lets sunlight pass through. Greenhouse gases hence act to warm a planet by trapping the radiation released by the planetary surface into the atmosphere, keeping the planet warmer than it otherwise would be, similar to how a greenhouse works, and hence the term greenhouse gas. Both carbon dioxide and methane have, and continue to be, rising in concentration over the last couple hundred years since industrialization and population growth has rapidly proceeded. This has caused a steady warming and changing climate of the Earth over the industrial period. Finally, we point out several species that are among the mix of air pollutants: carbon monoxide and nitrogen oxides, or NOx, which are a large part of automobile exhaust and other hydrocarbon fuel combustion; sulfur dioxide on the bottom of this list, which is due mainly to coal combustion and can lead to acid rain; and more esoteric species such as ammonia and hydrogen sulfide, which have strong familiar odors. Notice that concentration levels of these air pollutants are very small, often expressed as parts per billion. However, even at such small concentrations, these gases can be harmful to human health. There are many other air pollutants besides these that we will cover in this class. So returning to our original photograph of the Earth from space, we can now add more based on what we just covered. Concerning structure, the overall depth of around 500 kilometers can be separated into 4 layers based on temperature profile: the troposphere, stratosphere, mesosphere, and thermosphere. Since density and pressure strongly decrease with height, most of this mass is within the lowest 20 kilometers, within the troposphere and stratosphere. Concerning composition, around 99% of the dry atmosphere is nitrogen and oxygen, with water vapor comprising between 1 and 4% if included. The remaining 1% is a mixture of trace gases. These can be subdivided to several inert gases, greenhouse gases, the most important of which are carbon dioxide and methane, and several air pollutants that will be the focus of the course in later lectures. Some links for further reading on these points are provided here. Related topics. We now present a series of slides to reinforce and present important consequences of what we just learned. One thing we discussed is atmospheric vertical structure. This image is another taken from Earth from space. However, this time from the International Space Station at Earth's sunset. This helps make more visual the atmospheric structure. The sun in this image is likely just below the horizon. Atmospheric gases scatter sunlight, and at different angles based on the color of the sunlight. Blue scatters more so than reds. Hence, as we transition upward from the surface, the troposphere appears red, since the abundant mass in the lower atmosphere very effectively scatter blue light out of the field of vision, leaving the red and orange light visible. As we transition upward to the upper atmosphere, we see the blue light scattered more efficiently. Eventually, above the atmosphere where there is no matter, no light is scattered, and hence we only see the blackness of space. This image is thus a great visual to focus attention on 2 main things we just covered. First, the abundance of atmospheric mass in the lower atmosphere and the different layers of the atmosphere, the troposphere, stratosphere, and upper atmospheres. We focus now on the troposphere. This is the lowest layer where we live, extending up to around 10 kilometers. This is also the layer where weather systems form. Shown here is an example of such a weather system, an intense, mature thunderstorm cloud. However, one can see that the cloud only extends up to a certain height. In fact, this level where cloud growth stops at around 10 kilometers is around where the troposphere gives way to the stratosphere above. We call this boundary separating the 2 layers the tropopause. Cloud growth stops at the tropopause because the change in the vertical temperature profiles across this transition. Within the troposphere, temperature decreases with height, a situation that does not impede vertical motion and hence allows vertical cloud growth. Within the stratosphere, on the other hand, temperature increases with height, which we call a temperature inversion. A characteristic of temperature inversions is that vertical motion is strongly inhibited. Hence, the cloud cannot continue to further grow upward once it reaches the tropopause, since air encounters the stratospheric inversion. This is the reason why weather systems tend to stay confined to the troposphere. We also learned about atmospheric pressure, which is the mass of air overlying an area. Typically, surface air pressure is around 14.7 pounds per square inch. Another way to express pressure is millibars. which is what meteorologists typically use when depicting surface pressure on a weather map. An example of such a weather map is shown on this slide. One can see that, in fact, the value of surface pressure depends on location, and typically over large regions such as shown on this map, organized into distinct areas of relatively low pressure and relatively high pressure. These regions are the low and high pressure systems that meteorologists often refer to. Note that on a different day, the map might depict low and high pressure systems at different locations compared to what you see on this map. The lines on this kind of a meteorological map are called isobars. Along a given isobar, the pressure is the same according to the label of the isobar. For example, the isobar pointed to by the red arrow on this map is the 1008 millibar isobar, meaning that everywhere along this line the surface pressure is 1008 millibars. On one side of this isobar, the pressure is higher than 1008, culminating in the high pressure center of over 1020 millibars in the US Great Basin. On the other side of the 1008 millibar, pressure is lower than this, culminating in the low pressure center of less than 996 millibars in the US Southeast. Low pressure tends to be associated with stormy weather, and high pressure with clear, calmer conditions. For this reason, high pressure tends to be more associated with bad air pollution episodes, since the stagnant air associated with high pressure systems tend to inhibit dispersion and mixing of pollutants, thereby leading to higher concentrations. We also discussed the composition of the Earth's atmosphere. We can gain further insight into this topic by comparing the Earth's atmosphere to the composition of other familiar bodies. Here, for example, we look at the composition of the Sun. The Sun is mainly comprised of two elements, hydrogen and helium, which are the two lightest elements in nature. As with any star, it is the fusion of hydrogen atoms into helium at the Sun's intensely hot, high-pressure core that generates its energy. This energy propagates into space across the solar system as sunlight. Another solar phenomena are solar storms, which occur periodically at the surface of the Sun and can emit a stream of charged particles from dissociation of hydrogen and helium atoms into charged particles during these solar disturbances. These charged particles propagate into space, a phenomenon called the solar wind. Upon entering the Earth's atmosphere, charged solar wind particles can disrupt communication systems. Solar wind particles also cause magnificent visuals in high latitudes called auroras. These images show examples of this phenomenon. What is happening is the stream of charged solar wind particles through a complex process cause a subsequent transmission of charged particles normally trapped in the Earth's magnetosphere in the upper atmosphere downwards towards the surface. This downward transport occurs mainly at the Earth's high latitudes. The nitrogen and oxygen in the air absorb energy associated with these downward propagating particles. This energy is then re-emitted by nitrogen and oxygen as purple-greenish light. In high latitudes, in the northern hemisphere, this is called aurora borealis, or the northern lights. At high latitudes in the southern hemisphere, this is called aurora australis. Concerning the planets of our solar system, their atmospheres are all much different than Earth's. Mercury, Venus, Earth, and Mars have solid cores and are called terrestrial planets. The outer planets, except Pluto, are gaseous, called gas giants. We can discuss the atmospheres of gaseous and terrestrial planets separately. A visual of the gases of the planets is shown on this slide, dividing between terrestrial planets and the gas giants. The gas giants are comprised mostly of hydrogen and helium. In fact, at one time, people referred to Jupiter, the largest of such gas giants, as a failed star, like the Sun, made mostly of hydrogen and helium, but never developing into a full star. While large, Jupiter's mass, however, is much, much less than the Sun, and therefore, although made of hydrogen and helium, does not reach the internal pressures and temperatures in its core to initiate fusion reactions responsible for a star's energy. Our nearest neighbors are Venus and Mars, which along with Earth and Mercury are among the terrestrial planets. In terms of composition, Venus and Mars are substantially different than Earth in being comprised mostly of carbon dioxide, with a small amount of nitrogen and only a trace amount of oxygen. Earth, on the other hand, has abundant oxygen. This begs the question of how Earth developed a rich oxygen atmosphere. We will discuss this shortly. However, for now, we focus on the consequences of these different atmospheres on planetary temperatures. The temperatures of Venus, Earth, and Mars are shown on this slide as T-OBS, expressed in both degrees Kelvin and Celsius. One may initially think that the warmer temperatures of Venus are because Venus is closer to the Earth than closer to the Sun than Earth. However, this is not the reason for the much warmer temperature. Instead, the hot temperatures of Venus are a result of the intense greenhouse effect caused by its abundant carbon dioxide and extremely high atmospheric pressure, about 90 times that of Earth. While Mars is also mostly CO2, however, its temperatures are much colder. This is due to its thin atmosphere, with pressure about 100 times lower than Earth's. So how did Earth develop oxygen? This is a result of the formation of life in the early atmosphere, around 1 billion years ago. Specifically, from early single-cell plant life, algae and such, the oldest forms of life on Earth. Photosynthesis associated with plant growth is a process by which carbon dioxide is pulled from the atmosphere. The carbon is then stored in the plant organic matter and cellulose, forming the plant mass. Much of the oxygen in the CO2 molecule that was absorbed from the air is then released to the air in the form of oxygen. In addition to CO2, plant photosynthesis also requires liquid water to occur. The formation of life on Earth occurred over many million of years, starting around 1 billion years ago. Through the evolution of life, much of the CO2 in our early atmosphere was removed, and oxygen in the form of O2 was released to the atmosphere. Nitrogen remained left over from the original atmosphere. The resulting atmosphere was one mostly comprised of nitrogen and oxygen. The abundance of oxygen makes Earth's atmosphere unique from all other planets. Since plant life requires liquid water, the initiation of plant life on Earth presumes existence of liquid water. This is the reason much of the search for life on other planets focuses on whether liquid water can exist on the planet. Animal and human life, in turn, requires oxygen for respiration. Since this is an air pollution class and much of the health risk due to air pollution is due to inhalation, it is worthwhile to look in depth at exchange of oxygen and carbon dioxide that occurs within the human lungs and bloodstream when breathing. This diagram shows details of the human respiratory system. One can see on the left the overall system, showing how air passes through the trachea into the lungs. As air passes through the trachea, it then branches off into bronchioles, into the lungs. The right diagram shows how individual bronchioles in the lung terminate into tiny sacs deep in the lungs called alveoli. It is at the alveoli where the air-blood boundary is, and where oxygen transfers into the bloodstream through capillaries surrounding the alveoli. Carbon dioxide in turn passes out of the bloodstream into the lungs, to be exhaled at this point. Many of the health risks due to air pollution result from inflammation of the alveoli, which adversely affects the air-blood transfer process. This slide presents the topic of asphyxiation, a state of insufficient oxygen for respiration. Between 19.5 and 23.5% of composition, oxygen levels are optimal. As oxygen levels get lower, however, health impacts begin to occur. Lightheadedness and nausea begin to occur at 14 to 16% oxygen content in the air. Between 10 to 14% fainting occurs, and below 10% there is a risk of death. Any gas in high enough concentration to displace oxygen to levels below 15% is therefore damaging. A common risk of asphyxiation to industrial workers is when they work with inert gases, which are often used in industrial processes where gas pressure is needed for certain processes but without any reactive capability. If this inert gas leaks into the air, for example, when workers maintain, inspect, or repair industrial equipment, the worker can breathe this and asphyxiate. Since inert gases are odorless, there is little warning that something is wrong to the worker. Finally, it is worth noting that while oxygen is needed for respiration and beneficial to life, it can be a corrosive compound. The most familiar example is rust, which forms when ferrous, iron-containing metals are exposed to water and oxygen. The weathering of geologic formations over time is also enhanced by the presence of oxygen.